This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is filling of tank. We're given an empty tank of a certain volume, 0.25 meters cubed. It's being filled with steam from a pipe at 0.7 megapascals 360 C. Now this problem works because the pipe pressure and temperature are unchanged during the process. We're going to use that assumption in our analysis. And the valve is opened and the steam flows in, and the valve is closed when the tank pressure matches the pipe pressure. We're going to neglect the heat transfer across our control volume. Our valve is inside the control volume, and we're looking for the final temperature and mass in the tank. Now our analysis is going to hinge on the fact that the boundary, the place where fluid crosses the control volume surface, is at the known conditions of 0.7 megapascals and 360 C. All right, we've got some work to do. We're going to take our mass balance, and we're going to keep the transient term, and we're going to integrate the mass balance from 0 to t here. When we integrate the time rate of change of the mass in the control volume, we get the final minus initial. We get the mass of the control volume at the end condition t minus the mass in the control volume at the beginning condition times 0. Well, this one's gone because we said that the tank is empty. Now on the other side, we've got the mass flow terms. This is mass flow in, and this is mass flow exiting. When we integrate m dot, we get m. This is kilograms per second. This is kilograms. There's an inflow, but there's no exit flow. So our mass balance reduces to two terms. We're also going to integrate the energy equation for an open system, and when we do that, we get the unsteady term becomes final minus initial. And as before, if the tank is empty at the beginning, then this term is not going to be active. Get rid of that term. We're told that there's no heat. The boundaries, the control volume boundaries, is fixed, and I'm going to say that the tank is rigid, so there's no work associated with the pressure volume work. The enthalpy multiplied by mass flow term, when it's integrated, becomes mass times enthalpy. Again, these are the terms associated with something crossing the boundary. And we're going to say there's none exiting. We get flow that's coming in only. So quite a bit of reduction here. The mass balance reduces to the mass in the control volume at time t is equal to the mass that flowed in. Let me say that in words. Final mass equals mass, I'll say, crossing the inlet. And our energy balance also reduces down to two terms. It says that the final control volume internal energy is equal to the mass in the tank times the enthalpy that crossed the boundary. I want to also use another relationship. I want to use that capital U for any state is the mass times the specific internal energy. I want to combine these to say that the mass in the control volume at time t multiplied by the specific internal energy in the control volume at time t is equal to the mass in the tank, the mass that crossed the flow boundary times the enthalpy of the inlet. Now the mass balance says that this mass here is the same as this mass here. So I can cancel these guys. And I have left that the internal energy at the end of the process in the tank is equal to the enthalpy that crossed the boundary. Let me say that in words. Final internal energy is equal to the enthalpy. I'll say enthalpy at the inlet. How's that? Enthalpy at the inlet. And the evaluation, the integral equation worked. The integration worked because this was constant with respect to time. That simplified our analysis. That's an assumption in the analysis. Okay, we can solve this thing now. We're looking for, I'll say A, we're looking for the T at time T in the tank. Well, let's go back to our energy equation. We can get the internal energy. We want to find the internal energy. We're going to find it by finding the inlet conditions. The inlet is at 360 C, 0.7 megapascals. We need a superheat table. We're going to go look at our superheat table and we're going to find the H value. Let's go find a superheat table. Here's a fragment of a superheat table. And this fragment, the superheat table, comes in blocks. And this block is at 0.7 megapascals. That's what we need. We're looking for enthalpy in kilojoules per kilogram in this table. And the temperature goes down this column here. We're lucky we've got the temperature that we need, 360 in this row. We'll come across, here's the enthalpy value at the state for the inlet pipe. 3184.7. Let's transfer that back. 3184.7, and this in kilojoules per kilogram. Now, this equation here says that that's the same as the internal energy in the tank at the end of the process. Given this, now we want to find the temperature. So now we got the final state. The final state, we know that the internal energy is 3184.7 kilojoules per kilogram. That's one property. We need a second property. The other property is that the final state, the pressure is known. We're told that it fills up until the pressure matches, so it's 0.7 megapascals. Now we could have worked this problem with any final pressure. We happen to let it stay until the tank completely filled up. But given this final pressure, now we have two properties. Let's go back to the table. Which table was that? That was table A4, and you're going to say which book, right? We can find, let's go look at that. And the value for U is 3184.7. Here's the table. Now we're coming in with a known value of U at this pressure. And the known value of U is 3184, here's 1312632, so the value is going to fall in between here, so the temperature is going to fall in between here. We're going to interpolate to find the value. And I'm also going to interpolate for the specific volume, which falls between 0.50 and 0.57, because I'm going to need that in a minute to get the mass. So let me do the interpolation, and you can check my work when you have time. So I'm going to find that under these conditions, this internal energy and this pressure, we get that the temperature interpolates to 534 C, between 5 and 600, and the specific volume interpolates to 0.5295, that's in meters cubed per kilogram. Now, that's the answer to part A, 534 C, but why is T final greater than T of the pipe? We said that the energy equation told us that the internal energy at the final condition was equal to the enthalpy in the pipe. Well, recall that enthalpy is a defined quantity. It's U plus PV. So U plus PV at the entrance goes to U only in the tank. So that says that there's PV work on the gas in the tank. And that's the source of the heating effect. All right, part B says, what's the final mass? Mass is the tank volume divided by the specific volume of the gas. the tank volume was 0.25 meters cubed. The specific volume of the gas is 0.5295, interpolated from the table. And the final mass is 0.472 kilograms of steam. Okay, one final thought would be, if you're a scuba diver, I can't spell today, if you're a scuba diver, and you go to the shop and you ask it to be filled, they always take the tank, here's my scuba tank, they always take the tank and they dunk it in water when they do the fill. Let's put a valve on there, put a fill line here. They put the tank in water so you can get a full charge of air. Because otherwise the tank would heat up, and a warm tank doesn't hold as many kilograms of air as a cold tank. So this heating effect is well known. All right, let's recap. The problem that we're solving is we're filling a tank from a steam line that has a fixed condition. So we've got a fixed inlet flow. When we integrate the energy equation, we get final minus initial on the internal energy, and we get flow terms on the other side. We had started with the tank empty, so the final energy equation says that the final internal energy is equal to the inlet, the mass that flowed in, times the enthalpy at the inlet flow. This kind of thinking requires constant enthalpy at the inlet to make this integral. This is the conditions under which we did this integral. When we use the tables to find the inlet state and to convert that into the final state, we found that the temperature was greater than the inlet temperature, and that's because of the pressure volume work caused by filling up the tank. And if when you go to the dive shop, you make sure that you get your tank in water to get a full charge, then all will be well.